So hello and greetings to the all the viewers. Today we will going to see introduction to practical finite element analysis. So in this video we will go through the complete overview of what is FEA. So from basics of FEA, from solution of engineering problem to the what are the elements which will come under FEA, like elements, nodes, stiffness matrix, how to form stiffness matrix, then different types of analysis, different types of softwares available for CAD as well as for a CAE, whether they are paid or free softwares. Then we will discuss different types of analysis, and then we will go through some of the examples of practical FEA. So keep watching this complete video up to end so that you will get the complete overview of practical finite element analysis. So now this slide represents the learnings in this video. First we will see the engineering problem solutions, then FEA in product life cycles, then we will go through the different numerical methods, then we will discuss about what is FEA and FEM, then we will go through the discretization of a problem, then degrees of freedoms, nodes, elements, types of elements, meshing accuracy, then we will go through the FEA stiffness matrix, formulation methods, and one of the example like a bar element example. Then we will go through the what are the different types of analysis, and then we will discuss widely used FEA CAD softwares like free and paid versions. Then we will discuss the practical examples of finite element analysis. So once you will go through this all the terminology, you will get the some of the overview of practical finite element analysis. So first we will discuss about the engineering problem solutions. So there are like three basic methods to solve any engineering problem. The first is nothing but your analytical method, and the another is like your numerical method, and then the next is nothing but your experimental method. When we talk about analytical method, it is like 100% accurate classical method which is closer from the solutions and applicable for a simple problem like cantilever beam, simply supported beam. You can take an example of Jeep-Crane. This PO is like a cantilever beam. So when the problems are simplified, or you can say the simple problems are there, then we can easily find out the output of that problem by using analytical method. When we talk about complex geometry, like if you consider this kind of complex geometry like complex gain structure or any other complex like compressor, blower, so in that case it is difficult to find out the solution by using analytical method. So then we need this another method that is called numerical method, which is like mathematical representation, approximate assumptions based method. Then real life complex problems are there, and the results cannot be believed blindly. There some sort of validation will be needed through by experiment or by analytical method. So under this there are like four methods: FEM finite element method, BEM boundary element method, FPM finite volume method, and FDM, that is finite difference method. So most of the problems are solved by these methods, that is called numerical method. Then third will come like engineering experimental method. When we try to solve, there are few examples of engineering problem solution by using experimental method. When we talk about strain gauges, sensors and accelerometers, that will give us the actual working of the equipment. So this experimental method is nothing but your actual belongs to actual measurement, time consuming as well as expensive setups are there, and applicable only in physical prototype is available. So results cannot be believed blindly. For that we at least need a 3 to 5 prototypes must be tested. So if you take the example of these thermal cameras which will detecting the temperature of this, so like that you can find out the solution, or you can see the temperature gradient by using these thermal cameras, or you can find out the displacement by using strain gauges, or you can find out the acceleration by using accelerometers. So there are like three major methods like analytical, numerical and experimental to solve any engineering problems. But most of the methods or most of the real life complex problem will be done by using numerical method. We'll discuss these methods in later sites. So as we saw about the second, that is numerical method is most widely used to get the engineering problem solution. So there are like four further methods are come. Like first we'll talk about FEA. So finite element method is a popular numerical technique used to determine the approximated solution for a partial differential equation. The applications are like linear, non-linear buckling, thermal dynamics, fatigue analysis. The another method will come your boundary element method. So in this it is more powerful, efficient technique to solve the acoustic as well as NVH problem. Just like a FEA, it is also requires the nodes and elements, but it only considers the outer boundary of the domain. So when the problem is of volume, outer surface are considered. When if the domain is of area, then only the outer periphery is considered. Then the third is nothing but your finite volume method. So FEA method is representing and evaluating partial differential equations as an algebraic equation method is used to many computational fluid dynamics packages. So basically it is used for a CFD or computational electromagnetics. The next we use a finite difference method. Like it uses the Taylor series to convert the differential equations to an algebraic equations. In this conversion process, higher order of terms are neglected. It is used in a combination with BEM and FEM to solve thermal and CFD coupled problems. So all these four methods use the to solve the partial differential equations by using their respective methods. Okay, so most widely used like FEA and your for CFD like FEM. These are the two methods are most widely used to get the numerical problem solved. So now the next question will come like whether all these four methods is it possible to solve the same problem by using four methods? The answer is yes, but the difference in the accuracy and programming is as well as solution time problem. Okay, so when we talk about FDM, it has the limitation with complex geometry, different material assemblies, different element combinations like 1D, 2D and 3D. And then next when you talk about FEA, it is quite useful, well suitable strain extraction within the 3D objects. The next method like FEM, it has use solving stress problem, but it is well suited for CFD problems only. Convergence and equilibrium is quite natural in that case. And then the last your FDM or sorry BEM, it will only consider the outer boundary and leads to the pure results when internal details like stress strains inside the 3D objects are needed. So all this may have the limitation, but you will definitely get the stresses or you can say the strain within the 3D object by using a FEA, which is most widely used method. So now when we talk about FEA, but where exactly this will lie, FEA. So we will discuss about FEA in a product life cycle. Okay. So here basically when we talk about product life cycle, we'll first start with the product specifications. Then your conceptual design will done. Once your conceptual design will done, then we will think about ergonomics as well as aesthetic look of that product. Then we will do the standardization of standards. Then we will go through the detailed design. Once our detailed design is done, then we will further discuss about the prototype development as well as your testing for that respective prototype development. Once the testing is done, then we will try to correlate that using simulations. So simulations will come at this point of view. Okay. Then once simulation is done, then we will go through the design for manufacture, design for assembly, and then final step is drafting. So as we saw that simulation is will come after the testing as well as prototype. But there are some of the cases or some of the industry which don't want to do the prototype and testing. So they just simply want to rely on a simulation. So what they will do based on the detailed design, they directly go to the simulation phase, and based on that simulation or FEA, they validate their design, and then they simply go to the design for manufacture and design for assembly. Take an example of pressure vessels, like once they have designed that pressure by using a standard, they don't want to do prototype, they directly go to the simulation phase, and then once simulation is done, then they can go to the design for manufacture and assembly. Okay, so like that your FEA will come, or it is said the mandatory in any product life cycle nowadays. Now we know that FEA is mandatory, but what exactly the FEA? So FEA is nothing but your numerical method or mathematical representation of actual problem, or also like it is an approximate method. So we'll discuss that in more depth. Like FEM, or you can say the finite element method, reduces the degrees of freedom from infinite to finite with the help of discretization or a meshing. So that is called nodes and elements. So basically what it will do, it will reduces the degrees of freedom from finite to infinite. Okay, so FEM, so what the F is nothing but your finite, so reduces the degrees of freedom from finite to infinite. Element, E belongs to the element, so elements, all the calculations are made at a limited number of points known as a node. The entity joining the nodes forming a specific shape such as quadrilateral or triangular is known as a element. Okay, and then the next term will come your M is belongs to the method. So the three methods to solve any engineering problem, finite element analysis belong to the numerical method category. So like that your FEM is you can say the explained or illustrated. Okay, then the next term, as we saw that FEA will down, but the discretization term is important. So what exactly this discretization? So modeling a body by dividing it into the equivalent system from finite elements interconnected at a finite number of points on each element called the nodes. Meshing is nothing but the discretization of a continuous system with infinite degrees of freedom to a finite degrees of freedom. We will discuss to one of the example, like consider the object. So if you want to this is what your rectangular trapezoidal shape object, and I want to split this object in a three different shape. You can see this is one, this is another, and this is third one. So all these three from single object we split it into the three object. That is called the discretization process, and these three objects are nothing but your elements. Then from these elements the outer boundaries, or you can say the outer portion, is nothing but your nodes. So for these three elements you can call 1 2 3 4 5 nodes are there. So basically by forming these three element nodes you will get one elemental shape, so that is called element. Okay, so like that when we have any objects in the life cycle, when we discretize or when we split that object from infinite to finite, then that is the process is called as a discretization. So when we talk about real life objects, simplified or idyllic physical models, and when we convert that using the equivalent mathematical model, consider any example of any blower or compressor which may have a real life or problem, then what we will do, we will discretize that by using creating a finite element model by doing a meshing for that. And then once your meshing is done, we will move to the next part of the FEA. Okay, so like that in any real life problem you just need to simplify that idealized physical model by using equivalent mathematical model to get the mesh done. Then the next term will come, that is very important, degrees of freedom. So the minimum number of parameters like motions, coordinates, temperature required to define the position of any states of any entity completely in a space is called as a degrees of freedom. When we talk about a single point, right, let's consider the point A, which is defined by two parameters like x and y. So these are nothing but your 2 degrees of freedom for this define at this point. When we talk about a line, when the line will come, then there we will need a 3 parameter to define this line along this for a point. So x, y and rotation. Suppose this line is in a cubical kind of structure, so in that case we need at least 3 translation as well as 3 rotations to define this AB line. So that is like AUX, UY, UZ. So displacement along XYG and rotation along XYG. So like that 6 degrees of freedom will come into picture. Okay. So the DOF is very important concept in FEA. We use it for the individual calculation points. The total degrees of freedom for a given mesh model is equal to the number of nodes multiplied by the number of degrees of freedom per node. So basically we should know that the given mesh model is equal to the number of nodes multiplied by the number of degrees of freedom. Okay, suppose there are like 6 degrees 100 nodes for this cube, so and having a 6 degrees of freedom for each node. So the basic equation will be 100 into this 6 kind of thing. Okay, so the number of degrees of freedom depends upon the type of filament, like 1D, 2D or 3D, and the family of the element, whether these are like thin shell, plain shell, stress, membrane elements, and as well as the types of analysis. Okay, we'll discuss this in later slide. So the nodes and elements, and we already saw nodes and elements. The total degrees of freedom for a given mesh model is equal to the number of nodes multiplied by the number of degrees of freedom. Consider this rectangular object in this rectangular patch. So here, like, number of nodes are infinite, total degrees of freedom are 6 degrees of freedom. So the total equations are like infinite into 6. So number of nodes into degrees of freedom per nodes. So here it is infinite, right? When we make it from infinite to finite by using a 1, 2, 3, 4 mode, 4 elements, which is having the number of nodes 9 and 6 degrees of freedom per node. So the total equation will be 9 into 6 is equal to 54. Okay, so what we did, from infinite to finite we made, so we got some equations. So there are like 3 types of elements: 1D elements, 2D elements and 3D elements. Okay, so the finite element method only makes the calculation at a limited number of points, or you can say the finite number of points, and then interpolates the results for the another domain. Suppose if what FEA does, FEA will do the calculation only for this limited number of points, and if you want sum up the your results at other than these nodes, then what it will do, it will do simply the interpolations. So we will discuss that the calculation at other points within the body. FEA is making all the calculations at limited number of points, but the question is how it calculates the value of unknown at the other body and between the calculation points. So this is done simply by using a interpolation. Consider the 4 quadrilateral element as shown in figure. So you can consider this a quad 4 elements uses the following interpolation equation. So you can see this is nothing but your interpolation equation. Suppose you want sum of the displacement at point this, so you can use this equation: a0 plus a1x plus a2y plus a3xy. So FEA calculates the value at the outer nodes 1, 2, 3, 4, 0, right? So from these nodes, if you use this equation, you will get the displacement or your results at other than this calculated nodes. Now this is what the 8 node parabolic got. So for that you can have an equation like this: a0 plus a1x plus a2y plus a3xy plus a4x square plus a5y square plus a6x square y plus a7xy square. So like that your parabolic 8 node chord interpolation equation is used. Now once your interpolation is done, then as we saw that there are element terms. So what are the different elements are available in the commercial software? So we will discuss that in this slide. So like there are 3 major element types, like 1D, 2D, 3D and other. So 1D are like one of the dimension is very large in comparison to the other two. 2D, like 2 of the dimensions are very large in comparison to the third one. And in 3D, like all dimensions are comparable. So other than this, there are also that few elements like mass, point elements, concentrated masses of the CG. So this element, suppose consider the example of a compressor base frame, right? In that case, if you want to simulate the base frame, then you don't want to consider the complete geometry like compressor, motor, air end. So what you will do, you will simply idealize that components by using a mass element, and that simply connect that mass element to the mounting location. So these are come under this category. So the 1D element like shapes are line elements. So the types like rod, bar, beam, and the examples are like long, sharp, beam, pipe, pin joints. When we talk about 2D, so shape will be your chord tria, R tria, and the elemental type like thin shell plate, membrane plate stress, plane strain, axisymmetric model. So like that your all 2D elements will lie under this. So the examples, or you can say the application, like thin shell plate membrane stress. These are the element type, but the practical uses are like sheet metal parts, plastic components, and instrumental panels. So the basically the sheet metal parts, you can take the example of bumper of your car, so that will come under this 2D category. When we talk about 3D elemental shape, so that will be like tetra, penta, hex, pyramids. So element type will be like a solid. So the transmission casing, any engine block or any complex geometry like crankshaft, so that will lie under this 3D category. Okay, then next term we will come like as we saw about other category. So that is nothing but your translation and rotational stiffeners, dampers like damping coefficient you can define, gap distance, stiffnesses, friction, and rigid like RB2, RB3. So this will come under this category. So there are like two major softwares are available in the market which are widely used, like Abacus and ANSYS. So in Abacus you can have an element type designation like S4R, shell 4 nodes reduce integration, B31 like 1D element, so beam 3D first order interpolation, so M3DR membrane 3D 4 node reduce integration. When 8 noded reduce integration, so it is defined by C3DR. When it is like your tetra, so it is like C3D4. So like these are the major element types used by Abacus elemental library. And when we talk about ANSYS FPDL, so there it is like for linear 2D, plane 42, plane 182, solid 45, solid 185. Similarly shell 63, 181, beam 344, 188. So and then when we talk about quadratic, so there you will find like a second order plane 2, plane 82 for 2D solid, 3D solid line 95, 186, 92, 187, and 3D shell like shell 93, beam 189. So like that elements are available in Abacus as well as ANSYS elemental library. We need to go through this. So this is one of the example of types of elements. You can consider this is nothing but your solid block which is connected with this plate. So this solid block is meshed using solid elements, that is called 3D elements, and this shell is meshed by using 2D elements. You can see between this, these are both are connected by using beam element, so that will come under the 1D element, right? And these are like as we saw about discuss mass idealization. So here you can put a mass element, and these are that rigid elements which are connecting to this 3D. Okay, so the types of elements are very important when we talk about FEA. Now once your element type is selected, but there one thing will come into mind, like how to decide the element type. So in that case there are few things which will come into mind. Based on that you can define element. So like three major things: types of analysis, your geometry size and shape, as well as your project time. So when we talk about types of analysis, so there are like loading conditions, whether it is static or dynamic load, and the material details, whether it is linear material or non-linear material. So basically linear, you like your steel or any other non-linear material will be like your plastic, non-metals are there. And geometry size and shape, like mappable, whether it is mappable or non-mappable, and your like whether it is 1D, 2D or 3D geometry. So like that the second term will come geometry shape and size. The another term is like project time, so the product's life cycle time and solution run time. Basically when you are suppose your product is belongs to the automobile category, so in that case we always need to think about the life cycle time, right? So based on that also you need to think about the element type. Okay, so these are the three major things. If you know these things, then you can definitely decide the element type. Then once your element type is defined, then you need to think about the accuracy. So we'll discuss that how to decide the meshing accuracy. Consider this is the sphere, your complete sphere, right? So if you split this sphere by using 3 lines, 4 lines and 6 lines and 8 lines, so the 8 lines will represent the more accurate shape of this sphere. So similarly, if you put few more lines, you will represent the more your accurate shape of this. So definitely if you increase the number of lines, you will get the more accurate shape of this. So similarly in case of meshing also it will be like this only. We'll discuss that through this T-pipe example. So this is what our T-pipe will consider. This is nothing but your bend radius. So we will consider this much portion and we will try to measure this point, this curvature or fillet. First we will try to put two elements, then if you see here it is not more accurate or not capturing proper profile. When we put few more elements, it is having a better compared to the two elements. When we put few more elements like 6-8 elements, then it is like capturing the curvature properly, right? And here if we put more finer than that, so it will be more accurate compared to the 8 elements, right? So it is similar. When we put the increase the number of lines, you will get the more accurate sphere. If you increase the more number of elements, you will able to capture the mesh lines curvature. But here one question will come into our mind, like how many elements then we need to put. So there also your engineering judgment will come. We'll discuss this through this graph. Horizontal line with shows the number of lines or elements, and vertical line shows the answer. When we increase the number of lines, it will give the more accurate results, like 100. Suppose if you put like 32 or 30, more than 30, it will give 100% accurate result. But if you put like 20 to 25 between, it will also give the 95% of accurate results. At the same time, it will reduce the times to get the mesh done. Okay, so we need to think about these things, like more number of lines or more elements, more solution time, 100% accurate results. But nowadays we don't want 100% accurate results because most of the things are time dependent. So in that case, we need to do the moderate mesh. We need to do the less solution time, and then we need to get the results by 90 to 100% accurate. So this is the most widely used methodology nowadays with the industries, because if you put more number of elements, ultimately it will increase your efforts and time. Okay, and also the solution time to get the equation solved will increase. Now we will talk about the FEA stiffness matrix. Like we saw the different element types, and then the linear equation, or you can say the equation of linear static analysis, is defined by this basic equation. As all of us know that F is equal to K into D. So here F is nothing but your forces, usually unknown, and K is nothing but your stiffness, this characteristic property of the element, and D is your nothing but your displacement, so usually unknown. If you know any two properties, like if you know the force, you can definitely calculate the displacement. If you know the displacement, you can definitely calculate the force. Okay, so this is the linear static equation which will calculate the FEA stiffness matrix. First we can formulate the stiffness matrix for a given shape. Then once it is done, then we will do the meshing 1D, 2D, 3D. Then we will get the solution done, or solution equations. Then after solving that equation, we will try to get these unknowns. Okay, so like that the process flow is there. First you need to formulate stiffness matrix, then meshing, then solving equation, and then find out the unknowns. So when we talk about stiffness matrix, so the stiffness and formulation methods are coming to mind. So we'll discuss that. Stiffness K is defined by force per unit length. So stiffness is equal to the force required to produce the unit displacement. The stiffness depends on the geometry as well as the material properties. Okay, so consider the three rods having three different materials. We had applied a same pull force for three different material. First is cast iron, second is mild steel, and then aluminum. So all these three, if we are applying the same force, but here question will come into mind, like which of these three rods having a higher stiffness. So here, as we saw, that stiffness is your geometry as well as material properties. So for the same rod and same force, your cast iron have a more stiffness compared to mild steel as well as aluminum. Okay, so because this cast iron is more stiffer than the aluminum as well as mild steel, and mild steel is more stiffer than the aluminum, so that's why stiffness is more. So there are like three different methods to solve this stiffness matrix. First is direct method, second is your variational method, and third is weighted residual method. So the direct method is easy to understand but difficult for a programming, while the variational and weighted residual methods are difficult to understand but easy for a programming point of view. So here like we need to think about which method is more reliable or which method is more suited. So the reason behind it, like all software codes either use the variational or weighted residual methods formulations. Okay, so here like the limitation of direct method is easy to understand but difficult to programming, but software does the most of the programming. So that's why variational or weighted residual method are most widely used by the software codes. Now we will discuss about the stiffness matrix for rod elements using direct method. As we saw that there are three methods, out of which one of the method is direct method to solve the stiffness matrix. So we will try to solve one simple problem like single rod elements which may consist of two nodes, that is I and J, which is fixed at one end, and other end at I node the force is applied. So A is nothing but your area, E is Young's modulus, and L is your length. So all of us know that there are like some relation between stress strain. So based on that we will try to get this force value. Stress is equal to force per unit area and strain is equal to change in length per unit original length. So from that we will get one equation, that is like F is equal to AE by L into U, right? So now we will try to use some equation, algebraic equation, like summation of forces is equal to 0. So if summation of forces is equal to 0, then we will try to find out Fi is equal Fi plus Fj is equal to 0. So from that Fi is equal to minus Fj. Now consider a case 1 where Ui is equal to 0 and Ui is equal to greater than 0. This point is greater than 0 and this is your 0, fixed one, so 0. So Fi is equal to AE by L into Ui. As we know that Fi is equal to this one minus Fj, so we will put a minus Fj value over here, so that from we will get minus Fj is equal to minus Fi is equal to minus AE by L into Ui. So like that, when we consider another case, right, when we will consider this end is greater than 0 and this end fixed, we will get the other alternative equations for Fj's. So these are the two cases. From these two cases we will get the two equations, like Fi is equal to AE by L into Ui minus AE by L into Uj. So here like AE by L is constant, so based on that we will try to form this stiffness matrix. So if these are like force matrix Fij having 2 by 1, and we will keep this common AE by L, and from that we will try to write stiffness matrix 1 into minus 1 minus 1 1. This is also 2s to 1, and here your displacement last term, that is Uj Ui. So like that we need to form a stiffness matrix, like first is your force matrix, another stiffness, and then displacement. F is equal to K into D. Okay. Similarly, when we consider a case of two rod elements, like there are two rod elements having a different characteristics defined by 1 and 2. If you apply pull force over here, first step we will try to get a free body diagram, right? So we will try to get free body diagram for this F minus F my, and here like F, because it is fixed, so we will get some reaction over here. Based on that we will calculate these forces, right? Now similarly we will try to find out these terms from this stress strain equation what we saw in two rod element. So we will get the stiffness matrix, or you can say the force is equal to stiffness into displacement, like this. Here K1 is equal to A1 E1 by L1, so this term what we discussed earlier. Similarly for this rod also we will get similar kind of matrix. So now we will try to merge these two matrices, try to sum from these two sum matrix. We will get one matrix, like if you add F1 F2A plus F2B, and last one is F3. So from that we will get this matrix. And similarly here first displacement U2A plus U2B is equal to U3, right? So when we add we will get some another matrix like F1 F2 F3. These are the forces value and these are the stiffness value, and this is what your displacement. So likewise we need to formulate the matrix X. First we need to formulate the equation, and then from that equation we need to form the matrix X. So then this FEA will going to calculate based on this matrix X. Okay. So if there are 3 elements, similarly we need to do 3, 4, 5, whatever the raw elements are there. Likewise, we need to form this matrices. Now we will discuss about the FEA process flow. As all of us know that FEA is one of the method to solve the engineering problem, but what are the processes involved in this? So first process is nothing but your pre-processing, where like geometry cleanup, simplifications, material definitions, meshings 1 to 2D 3D, loading and boundary conditions. So like first phase will for you need to create your FEA model for the solutions. So that is called pre-processing. So geometry cleanup, like if you don't want complex kind of feature like chamfers, fillets, or any unwanted hard edges, you can clean up that or remove. Then you can define a respective material details, and then you model. If you create a FEA model based on 1D, 2D, and 3D elements, and then put your loading and boundary condition. So this is nothing but your pre-processing. Once pre-processing done, then next phase will come your solution, or called as a analysis. So here like the major things like what are the types of analyses, what kind of software we need, then is there any additional steps are there, and then solution set. So these steps are come under solution. So once the solution is done, the next step will come right your post processing. So post processing is nothing but your result extractions, right? So here like stress strain plots, stress linearization for pressure vessels, and graphs if you want. So this is nothing but your result extraction and validation phase. So complete FEA process is defined by 3 terms: pre-processing, where the geometry cleanup and your FEA model creation is done; then solution, where we will fire the run, and then next is your post-processing, where we extract the results and validate with the design. So these are the major steps to do with any kind of FEA problem, right? Now we will move towards as we saw that FEA process flow. Then as we saw that there are second term like solutions. So here that we should know about what kind of analysis are do, because FEA belongs to the different analysis terms. So what that analysis? So we will see in this slide. So first and very important, nowadays most of the industries are doing static analysis. So static analysis is nothing but your simple linear analysis, right? So here like static loads will come like pressure, dead weight, forces, all these things will come over here. So under this like linear, non-linear is like based on your context non-linearity, geometry non-linearity. Then it's quasi-static when there is a small times of force was there. Then contact bolt joint simulations, then leakage analysis. So these analysis will come under the static analysis phases. Then your dynamic analysis come, dynamic vibration analysis comes. So here like first we and basic analysis, your model analysis, from where we will get the number of mode shapes and your natural frequency of the product. Then next your transition dynamic analysis, here like transient loads are there, then frequency response, then spectrum analysis. This is also called response spectrum, like seismic analysis, and then your multi-body dynamics. So these terms comes under the dynamic analysis. Then next we like explicit dynamics analysis. So explicit dynamic is nothing but when there is a small impact is there, drop, trace, can crush, projectile impact, car crash analysis. All of us know that car crash analysis. Impact also I think most of the people knows, like mobile drop from certain height. So like that these terms are come under the explicit dynamic analysis. So here basically the force is there, whatever the load is applied, but at a very short instant of time. Then next term will come your fatigue and durability. So in this case, like as we know that fatigue is nothing but your repetitive load which will comes for any equipment. Consider a case of pressure vessels where it is subjected to different duty cycles. So due to repetitive duty cycles, there some sort of stresses are developed, right? So that is nothing but your fatigue stresses. So here like stress life approach, strain life approach, ASME standard fatigue analysis, DNV standard fatigue analysis. So like that, this analysis will come. Then thermal analysis, like all of us know that when there is a temperature loads are there, so the steady state, transient with respect to time, if thermal profile is varying, then coupled thermal stress analysis. Transient weld also is there, like while doing welding there are some high residual stresses were going to develop due to contraction and expansion. So these are under the thermal analysis. Then next term will come like optimization, right? This is also most of the important terms which is nowadays used by most of the industries. So the topology optimization, size and shape optimization, topography optimization. So all these terms are come under optimization. Basically topology means if you apply some sort of force on a cube, based on that force you will get some sort of profile where we need to add a material or where we need to remove the material. So if you remove some material, then based on that load path profile we can create a geometry from that cube. So this is come under topology. And size and shape, like if you have 10 mm of thickness and if you want to reduce, then that can also be done for respective loading and respective thicknesses. So you can vary the thicknesses based on your loading, right? And then your topography means there are some sort of beads or speed patterns you need to add. So like that, this software will tell us whether you need to add a patterns or kind of thing, so that stiffness will increase. So that all these things will come under the optimization. Then there are like high-end analysis. We know that like mold flow analysis, multi-physics analysis are also there, like fluid structure interactions are there. When any CFD based analysis, CFD plus FEA analysis will come into picture, that is nothing but your high-end analysis. So multi-physics, like take an example of any pressure vessel. So pressure vessels, suppose the transport loading condition, when it is loaded on the vehicle, what will happen if suppose liquids are there, due to sloshing, there will be some sort of vibration will going to come, and due to these vibrations or sloshing loads, their stresses are developed. So that is come under fluid structure interactions, right? So multi-physics are there. And NVH is also this noise, vibration and hardness. The next last term will like CFD, that is computational fluid dynamics. So here, like if you wanted to know that pressure drop ratio, flow characteristics, cavitation study, and thermal transient flow analysis, laminar turbulent flow, flow coefficient, pressure recovery. So all this come under the computational fluid analysis. So this slide is nothing but a brief view what are the kinds of analysis are available and in the commercial software. So all the analysis will come under this so 8 tabs. So right. So if you get a chance to go through each and every in depth, then you will come to know what exactly these are. Okay, when you try to solve this, then you will get the more idea on this. Then next, as we know that there are different analyses are there, but for this distributed analysis there are also different softwares are available in the market. Like when we talk about CAD softwares, there are like commercial CAD softwares are like mostly use AutoCAD Inventor, Autodesk, the product of Autodesk, then Creo, product of PTC, Unigraphics, product of Siemens, CATIA, SolidWork, Spaceclaim, MicroStation, Bentley, Onshape, TurboCAD Pro. So these are the commercial softwares, and there are also free softwares, or you can say open source are available. So you can get if you don't have a license for this, then you can refer this license like 123 CAD, LibroCAD, FreeCAD, BRL CAD, OpenSCAD, QCAD, and SolverSpace. So these are the free softwares available. You can download that from easily Google. Then CE softwares, as we know that ANSYS, Fluent, CFX, Abacus, Naston Patran, Hypermesh, Radius, LSDyna, Simufact welding, this is for welding, Autodesk CFD, Mold Flow, Modex 3D, ANSA, Cosmol Multiphysics. So ANSA is also like pre-processing software, and also will come like Hypermesh kind of thing. These are pre-processing. So, and these are like solvers, Abacus, ANSYS, Naston Patran. And there are also like free or open source software available, C softwares. When we talk about Calculix, GCM suits, ANSYS students versions are available for like 32,000 nodes. Then FE Bio. So this is basically biomedical engineering. Then FEA Fit Flow for CFD, same scale. Then your Z88 Aura. Then FITSE. This is also like academic version. If student want to refer, they can refer this Visual FEA educational version, and CE Plex also free plan available for this. Okay, so these are like commercial as well as free softwares available or widely used in the industries. Then we will talk about different examples, or we will go through some of the examples of this FEA. Okay, so first example is like thermocoupled structural analysis of shell and tube type heat exchanger. So we will go through this. This is what your heat exchanger, that is called shell and tube type heat exchanger. And for you can see that once we will apply a temperature from shell side and tube side, you will get this kind of profile. So your temperature, this is the body temperature plot. Here like temperature is varying from 200 degrees centigrade to 159 degrees centigrade. So 200 will be on the shell side, and here like tube side. So all of us know that what is shell side and tube side. Let me explain that. When the fluid will enters into this, like from this, and it will go to pass through this area, tube side area, and also inside the tubes, that is called the tube side. And shell side is nothing but when the cold fluid will flow through this, and it will pass through outer the tubes, and it will move out from this, that is called the shell side area. So like that, there is a two different fluids are there which is having at two different temperatures. So for that we need to do this thermal simulation, right? And this is what your equivalent stress is for that, and you can see how it is viewing for that respect to temperature load. Here it is fixed, and along this fixing it is try to expanding due to the temperature difference. And these are the stresses. So you will find over here like maximum stress are will going to find your here, because there will be the more temperature gradient at these junctions, that is called the tube sheets. Okay, so this is one of the example of thermocoupled structural analysis. Once your thermal loads are applied, there are also some additional pressures are there, like similarly shell and tube side pressure. So that's why it is called thermocoupled structural analysis. So first you need to follow the thermal analysis, then you need to couple that with the structural analysis. In structural you can apply a pressure loads. Okay, the next example we will discuss about the hot box analysis of Naphtha stripper vessel. This is also belongs to the pressure vessel category. So here like if you see, this is one of the 3D model, or you can say the Naphtha stripper vessel. So here like we will do the axisymmetric like 2D analysis. First we saw the 2D, 3D. Now we will going to see the 2D analysis. For that, but this model is axisymmetric along the center axis. So we can extract this 2D shape, and then we can do the simulation. So it will save our time, as well as we will get the less effort to do the meshing, right? So you can see this is nothing but your shell. In between skirt is there, this is outer insulation, and this is inner insulations. So this portion is nothing but your Hawks ball. The purpose of this hot box is nothing but because this shell are subjected at a very high temperature. So this high temperature should be passed out to this. So due to this radiation, or you can say due to this hot box, it will going to pass to these strippers, right? So that's why you will get the very less stresses at the junctions. So that's why these hot box are provided. Now you can see the imported body temperature. Once you will do this thermal simulation, you will get the temperature profile like this. You can see, right? And these, once the thermal is done, then you can do this static analysis, where you will going to apply the G loads, your pressure loads, internal pressure on this vessel, right? And that compensating pressure at the opening, because we haven't considered complete portion, so that's why we need to apply this. And this is what you are due to this pressure loading, you can see the deformation, how it is deforming kind of thing. So it is trying to moving out, or you can radially expanding along the this fixed locations. Okay, so here and the due to temperature, as we can fix from this, and due to temperature it will try to expand, and due to pressure it will try to move out, right? So like that, once you will apply the loads, you will come to know this kind of profiles. Okay, then next problem we will see one of the example of raw water pump experience high vibrations and a failure So raw water vertical turbine pump, that is called raw water vertical. You can see this is nothing but your actual configuration, and this is what your raw water turbine pump. Okay, so you can see, first I will put all the plots so that you can able to see how it is deforming, how it is vibrating. If you see one of the example of this, first with this position they might getting the, you can see the the natural frequency, and your mode shape will be like this. So you can see the animation, it is right here. Also you can able to see the submerged portion of this, which is vibrating and having a frequency of 5.14. so these plots belongs to the respective mode shape, which is having frequency 5.14, right? So this might be exciting with their operating frequency. So once your natural frequency will excite with your excitation frequency, then your resonance will going to happen. So for that, if you see, this model belongs to this category, original discharge head. So what they have put it, they have added these ribs, you can see these ribs, to get the additional steepness at this pump locations. So once that is done, then they will get the some sort of shifting from this frequency, right? So you can see this the virtual displacement plots. So like that, when you come across the some of the vibration simulation problems, when the problem belongs to the coinciding with natural frequency, so in that case you need to put some sort of additional ribs, or you can strengthen that model so that we can shift that frequency from the natural frequency, right? So we will reduce the chances of the resonance in that cases. So this one of the case study I had refer from this reference. You can go through this reference for more detail. Okay, now next case study, this is also very interesting, like topology optimization of engine gearbox mount casting. So here if you see, these are the one of the example from Audi. So they used to do this topology optimization. If you see, consider the design phase. This is what the initial model, and then you need to apply a load and fix this. Based on that load, you will get some sort of profile. Now you can see the weight, loads, material, design space, manufacturing. Here you can put the manufacturing as well as design constraints. So design constraint is nothing but you are fixing location. Manufacturing constraint means if you want to some of the reefs you want to keep for a manufacturing point of view, to get the strength point of view, so you can define that as in under the manufacturing constraints. Once you will get the defined profile, so you can further create a geometry design with respect to the optimization result, like manufacturing cost. So from this you will get this kind of profile, and from this based on this profile you will create this kind of geometry, and then you will get the final shape like this. Analysis and design optimization in detail. Okay, so if you see initial geometry and then later on geometry, you will find a lot of material is reduced, so it will be ultimately saving the cost, right? So like that, this optimization will going to work. So this is also I have taken some Audi reference. Okay, so we will go through the another example same of topology, because this is very interesting. This is also from the same PDF I have taken this example. If you see, this is nothing but your torque cross member from the powertrain mounting system of Audi A4 and with 4-cylinder TDI, right? So here if you see, this is what your initial design space, and based on that they have got this kind of profile. So based on this profile they designed this geometry and further did the validation. Okay, so you can see the different processes, and based on that you will find that lot of material reduction. So here like weight reduction by approximately 3 kg, so it means like 57 kg%. Steepness of jet might increase by 13%. So cost of the products are reduced significantly. So if you compare, this is nothing but your comparison. Your weight 100% earlier, now it is like 43%. Cost also reduced like 45%, and steepness will also increase. So all three parameters are showing the increase in your steepnesses and reduction in your weight as well as cost. So like that, when you talk about weight reduction, then you need to think about topology optimization. Okay, so these are the references from where I have taken this complete video, or you can say I had captured this video based on these references. The first will like practical aspect of FEA case study, then finite element stress analysis, then this is what one of the PDF from where I have taken this reference. So these are the major references from where I have created this complete video. So hope you guys have liked it, and I had used ANSYS 17.2 version. So thank you guys, thank you for your time, and thank you for keep watching this. Okay, hope you will have like, please let me know if you have any questions on this. I'll happy to help you in depth.